do it when we're here?
No, it's fine. We can. We'll just
throw ourselves by.
Sure, I can introduce myself.
Sure. Well, I'll just say thanks everybody. Welcome to a special PL Wonks where we're happy to have Germane, who's going to talk about his work on control flow analysis, and thanks for coming and bringing all of us together on at a surprising time of year for us all being here at a Wonks talk. But yeah. Take it away.
Okay, thanks for coming during the off season, and yeah, thanks for letting me give you a talk. So the theme of the talk is basically going to be about a dimension of analysis design, which is, should your analysis be more or less oriented toward how a human operates? The answer is not always to be more like how a human operates, but I'm going to kind of make the case for control flow analysis at this point. That's where we should go. So I just want to take stock. How comfortable are you with control flow analysis on a scale from 0 to 10? 0 being you've never heard of it, 10 being you're all in sugars.
1.
1? Okay.
5.
5.
Go with
okay. 2.
8.
Okay, great. Okay. I don't want to waste your time, so that's great. Okay, so let's talk about kind of the status quo where we are today. I assume you're all comfortable with S expressions, which is not the case for all of the audiences. Okay, so here we have, factorial. It's written in CPS style. I actually took this example from a paper on higher order optimizations by Lars Bergström. But I just want to use this example to illustrate how what a control flow analysis is and how it's obtained in analyses today. So the analysis, in the end, is a map from every sub-expression of the program to some conservative approximation of the values it will take on. So what you see on the bottom half of the slide is part of the analysis, and it's not all of it because let's see, my pointer works. Actually, can you see my mouse? No.
Well, you can just point.
I'm just going to point at the screen with my hand. I mean, like every sub-expression has some value associated with it. The fact that this is a CPS program kind of makes things weird, but those would be in the analysis to this map. And this program was actually not a program because it's got a free variable h. So this is some sub-expression in a larger program. And if you wanted to analyze this program with an analysis today, you have to say what you needed to do with h. When you encountered h, it's free. You don't know what it can be bound to. And there are different techniques available to do that soundly. But that's kind of what analysis looks like. Any questions about that? Okay, so not only is this what analyses look like, but basically every analysis is going to come to this in roughly the same way. And that is, it's going to mimic concrete evaluation. It's going to start with the entry point, and it's just going to work its way through. And the difference between the abstract and concrete evaluation, I mean, there are some fundamental differences, but basically it's going to be intercepting recursive calls, finding a fixed point, that kind of thing. So that is the status quo of control flow analysis. So I want to present a different kind of analysis to you, called demand control flow analysis, which is inspired by demand data flow analysis. So I want to go back to this program and highlight this variable k and ask the question, what could flow to k? At the risk of undermining the title of my talk, I want to know, how would you as a human answer this question? Like, could you give me a step-by-step process of your reasoning? Yeah.
So we look at where k is bound, which is in the lambda, and then we see that this lambda is fact, and then we look at all the places where fact is called, and then we say, okay, the third argument to fact is the things that flow to k.
exactly. You could have invented demand CFA. This is exactly how you would do it. You say, okay, well, K is a reference, so that means it's going to take its value from a binding. So you say, oh, it's the third parameter of this lambda. Well, where is this lambda applied? And so these arrows, they indicate not the flow of values, they indicate the attention of the analysis. So step 1 is to see that K is bound as the third parameter of the lambda. Step 2 is to see that the lambda is bound to fact. Step 3 is to find a reference to fact, and it turns out it's in application position. Step 4 is to take the third argument of that application, look at it, see that it itself is a reference, and see how it's bound. We've been here before. We have looked, we've already asked the question, what is the third parameter of this lambda? So now we're going to go on a different branch, tracing out fact. This would be arrow 5. We find the fact in the body of the Lebesgue, and then you come to this lambda term. And you're done. So like regular control flow analysis, this is defined in terms of a fixed point. And there are join points and things like that. But we did not have to say what happens when we encounter H. We didn't encounter H. We didn't know we wouldn't when we set off on this. But we were able to basically do this analysis on a sub-expression of a program, an incomplete program fragment. Okay. So I want to just do one more example that's very similar. I won't go through it in excruciating detail. So we've got this function try, which the reason it's called try is because if you fed it the list 1, 2, 3, 4, 5, it would feed you back the first 5 triangle numbers, and it's going to use map. This is just a standard definition of map. And I guess the important thing to look at here is just the interesting part of the computation where you're going to map, and the list you're going to map over is itself computed by try. It's a recursive call. So suppose that we're going to inline map, just to make things a little bit easier. So same program, but with map inline. And then we're going to ask the question, can we inline at this call site? And so that means we need to determine the value of f, first of all. But in a higher order language, just knowing the value of f is not necessarily enough. So we do the analysis, and we're going to determine that it's this lambda here. Now this lambda has a free variable, y. And in a higher order language, because you have free variables, it's not even enough to know that the free variables are in scope of the call site. It may be that they have different bindings at the closure creation site as they do at the call site. And so you need to perform environment analysis to justify inlining this lambda.
Okay.
Yeah.
Is y totally free? Should it be x?
Oh yeah, maybe it should be x.
Okay.
I think we're supposed to be.
No. Oops.
So,
Yeah, my bad.
Can you go back a couple?
yeah.
It should be x. It should be x.
Okay.
Yeah, because y is not in scope there, obviously. I changed x there. I'm sorry. So it should be plus x.
Thanks.
Okay. So, there are like a handful of theories of environment analysis that you can use to do this.
And the answer is it can be inline.
The answer is it can. Yeah.
And because x is just the same x everywhere
Well,
in this case.
yes.
And because the lambda gets immediately applied, so we don't need to worry about.
Yeah. Now, here's the thing: during evaluation, when you make this recursive call, there's another binding of xk.
Yes.
And so there are co-live bindings of x, multiple co-live. In fact, arbitrarily many. It depends on how many are in the list to begin with, the length of x is. And so you need to perform the analysis to make sure that the bindings are the same.
Right, but this is the easy case because it's even though that there are lots of bindings of x's, we're always just looking at the most recent one.
Well, okay, I mean,
In this particular case.
No, that's the thing is, it does look easy, like it is the easy case, except that most theories of environment analysis will not be able to justify it. And the reason is because the control flow analysis is going to explore this call, and it's going to find more bindings of X, co-live bindings of X, and it's going to say, okay, I can't, like yeah. So, this is a place where the demand approach can have an advantage. And that is if you build an environment analysis that only, that can look at where the control flow analysis has worked. And if you have a theory, that is, of environment analysis, that can say if the control flow analysis didn't need to explore that area of evaluation, then it's not relevant. And so we have a theory that's built into demand CFA where we can do that. And you can justify this very, like it's so obvious to us that you can do that you should be able to inline here. And the theory that we have justifies it. That was a great explanation, sorry. But, okay, are there any questions at this point? No, what's going on? Okay. One final technical piece I want to talk about is context sensitivity. So KCFA, which is like the quintessential control flow analysis, it's sensitive to the K most recent calls in the call trace. So if you just had a log of all the calls, it's the K most recent in the log. And that is not a good fit for a demand analysis because the demand analysis is not going to visit all of evaluation. So it's not going to have that entire trace. And so a better fit we found is something like the top M stack frames. And there's one more complication here for achieving context sensitivity, and that is the whole intention of demand control flow analysis is I should be able to point to a spot in the middle of the program and ask a question about it. But what is the context in that spot? So what the analysis needs to do is not only answer the question, but determine the possible contexts in which those answers could be. So we have a paper on this, on how to do it. And so what happens is if you look at this program where we've got a curried version of apply, we would hope that context sensitivity would allow us to correlate the arguments add 1 and 42 and separately sub 1 and 35. And by keeping track of the top M stack frames and instantiating environments in a particular way, we can do it. So at this point, we've got control flow analysis, we've got context sensitivity, and we've got environment analysis. So we have sufficient theories to do like standard control flow analysis. We've now sort of met the status quo, like we can do what KCFA can do.
So what is M here?
M
So
is like
parameter.
K.
So there's going to be some, it's like MDCFA.
Sure.
Okay.
So like we could have 0 or we could have 12.
Yeah, it's the number of stack frames that you will keep track of. You're willing to keep track of.
So what's the difference between the K most recent calls in call trace and the top K stack frames? Is it about calls that have returned or?
Yeah. So suppose that you make 2 calls in sequence, F and G.
Okay.
And suppose that the demand control flow analysis is asking a question about the call to G.
Right.
Okay, so let's contrast these 2 things.
Right.
In KCFA, when you're looking at the call to G, the context is some of the calls made in F. And in the demand setting, you don't know what those calls were, and it feels wrong to go analyze the call just to see what the context would be, to go see what those calls would be. If instead we said, we're going to keep track of those top stack frames, the top stack frames are the same for the call to F and the call to G. So we don't need to go explore into F to figure out the context. Is that
Yeah, it sounds equally wrong in KCFA. Maybe again, I said 1, right? So in KCFA, it also feels like why do you care about the calls? You call me to F if you're just analyzing G.
Oh, I see. Oh, yeah.
the
I-
opposite polish versus.
Depending on the day, I share your. Yeah.
It falls out more naturally from the CFA formulation though. To care
It
about
does,
this.
and it's sort of like, so CFA was originally small step semantics, and that feels very natural. There have been big step formulations of CFA that have come since then, and then people have reproduced KCFA, and there it's sort of like, I don't think that's exactly the right thing to do. I actually am coming around to the idea that you should not be call sensitive at all when you're analyzing a recursive function. If you're interested in hearing more about that, I'll talk to you offline about it.
Yeah, so, I mean, there's one interesting thing in the KCFA literature is that there's lots of things where you can reproduce something fairly similar to 0 CFA. And then you can see there's something that's sort of like the recent calls, and you can truncate that to some bound K. But it is usually the case that the thing you first started with was not exactly going to give you the same answers as Owen's dissertation for 0 CFA, and then the truncation to the K things that you're considering are not going to be exactly the same as the K things that he was considering. And so you get something that's has some exponential precision trade-off in this K factor, and that doesn't consider any call history at the 0 case, but is like not exactly the same in any sense to what the original literature was, and then we call them all KCFA.
Yeah. Here's an interesting specific case. So KCFA is exponential for K greater than 0. That's when you do it like on a functional language. But KCFA was ported to an object-oriented setting, and there KCFA is polynomial. And so Matt Might and David Bedhorn and Yannis Meridakis, I think, they wrote a paper about this, and it comes down to the way that environments are constructed, the difference in the way they're constructed. It's explicit and object-oriented. It's implicit when you create a closure and functional. And it's the number of environments, the distinct environments that leads to the difference. But anyway, just kind of to Sam's point, the formalisms look the same, but there are just these subtle differences that totally change. Are these both KCFA? They have such different characters.
Yeah, but even in situations where you're like characterizing the lambda calculus and 1 CFA is exponential, like it can be, so like my pick, if you take the abstracting abstract machines paper, like the 0 CFA that you get out of that is not the same, doesn't give you exactly the same answers for every program that like Owen's dissertation does.
Right.
And if you make it if you take 1 CFA, it doesn't like do exactly the same set of things. It's just, but it is exponential in time. And I mean, and a lot more precise, but like not in exactly the same way as any of the other formulations of this in the literature. And similarly, if you do big step versus small step, like you were saying, you have to work really hard to turn the natural thing into a thing that gives you exactly the thing that some prior paper was giving you.
Yeah. Okay. This is the end of the technical part of the talk. So are there any other technical questions or technical things you want to talk about?
So do you get the precise answer here with 1 level of context, 0 level, 0?
1 level is enough.
Okay, 1 level gives you this. Okay, that makes sense.
Yeah. Yeah, 0 is not enough, but 1 is.
And the 1 is because it's curly?
The 1, it's because it's not the currying, I don't think is relevant to that. I pulled this out of a paper, and the currying was specifically something else. But the 1 is enough so that when you see, you're going to say what call site was called this here, and it's this call site here, or that call site here. So you'll have a correspondence between where F was bound
and the call is made.
It's possible that you can think about it being caused by the currying, because if you think about this in ML and then you uncurry it, then there's only one value that flows, which is the pair of add 1 and 42, or the pair of sub 1 and 35, and then you don't get confused anymore because you're confusing the two call sites, but you have two values.
It's even worse than that. The currying really was a red herring, so I really should I'm going to go over this example and take it out. Even if it was not curried, 0 CFA would confuse them.
Well, sure, but it's the two arguments thing that would separate them, whereas if you, depending on how you formulate, if you tuple your arguments as a pair, the way you might in the sort of natural way to write an uncurried version of this in standard ML, and then you do the analysis, you will get a flow of a pair, and you will only get two elements each. So what happens here, to be imprecise, is F is a 2-element set of add 1 and sub 1, and X gets a 2-element set of 42 and 35. But there's no relationship between the sets, they're sets. So it says that the possibilities are, but if you tuple everything, then you get one 2-element set for the things in your tuple, and but then depending on exactly how you do the projection, maybe those projections get two values, and then you lose the precision. Yeah. So it's.
But I guess I'm still worried about because apply add 1 is there's going to be some lambda. Am I not the two different calls to apply? They're not getting two different lambdas that do not get either more confused or less confused by the fact that it's curried in this way.
What you see is that the thing that flows to apply is the same thing in both cases, which is just the lambda f. And then you see that the thing that flows to the result of that application is apply lambda x with an environment where f is bound, and f might be bound to add 1 and sub 1.
Yeah.
And then the thing that flows to that application that Kimball has highlighted is, and that expression with f being bound to either add 1 and sub 1, and x being bound to either 42 or 35.
May I say that your claim is that since there are two usages of apply, and therefore two usages of both f and x, and for example, if we consider f, in the first case, add 1 flows into f, and in the second case, sub 1 flows into f, and therefore, when we do static analysis on f, what f is such a question. The answer for such a question is imprecise because it can be add 1 or sub 1.
Right.
And that's your conclusion.
I wouldn't say it's my conclusion. That's what 0 CFA gives you here. And if you add one level of context, then you distinguish those two call sites.
And you mentioned the tuple case. Do you mean that in that case we can distinguish different occurrences of apply? Is that what you?
No, it's that if you pair up add 1 with 42 and sub 1 with 35, and then you call some function that takes a pair as arguments, then that function we will get a confusion which says that function might take two different inputs, just like there might be two things bound to f, but those two things will be the two pairs. But then if you project out of them to actually do anything, then that projection expression will get two different values, and the second projection will also get two different values, and you'll be back to that same issue. And so if you
Tutoring doesn't help, right? The concurrent conclusions.
well, it depends what your semantics. It depends if you just rewrite it by tupling and then immediately untupling, then it won't have. But you could imagine something where
Yeah, I'd say at least it's going to be fragile because it's going to depend on exactly what kind of binding
Yeah.
behavior you have. The context sensitivity will just make it a little more robust to those kind of PTSD
Yeah.
analysis.
Yeah. Whereas if you have one level, there's 2 calls, they're distinguishable. So.
And the 2 calls happen on the frame, the caller's
Yeah.
frame, so you add 1 level,
Mhm.
then you're good. For sure.
Okay.
I guess I have a question about,
Okay.
so this is my first time sort of hearing about the demand CFA kind of stuff. And so, so it sounds, I mean, tell me a little bit more about it. Like, so there's like a bunch of papers about it, there's some implementations, or is it brand new, or where are we
There are
at?
a couple papers about it.
And is there some empirical, like, results, some, like, how does it do? You piqued my interest, so.
I'll tell you, not published. So I wrote a paper a little while ago where I looked at Racket. So, will you kick this question off to the end?
Sure.
Because there's some stuff we're going to talk about, and I can it'll dovetail right
Okay,
there.
sure.
Okay. So, and I want feedback and pushback here. So at this point, hopefully, you have an intuitive understanding, at least, of the difference between control flow analysis, status quo, and demand control flow analysis. And now I want to talk about why I think demand control flow analysis is, the right tool for the time. So the promise of CFA 35 years ago was a generic framework that you instantiate with your semantics to get deep semantic information about your work programs. But the reality has been that it's just expensive. And it's expensive in many different ways. So this is not all of the ways, but we mentioned how KCFA is exponential. MCFA was a way to realize a polynomial hierarchy of analyses. There have been other variants like sub-zero CFA, which gives up a lot of precision to make it linear. And then there's been work in getting higher control precision without any hit on your complexity. So there's been a significant amount of work in addressing just the fundamental complexity of this. Okay, now these 3 things, derivation, construction, verification. Basically, how expensive is it if you've got a problem and you say, well, I want to write an analysis, a control flow analysis, to prove these properties, give me this information. So it used to be that you just had no help, you had to be an expert, and you used your intuition to build something, to maybe formulate an abstract semantics. And then you prove some relationship with the actual semantics of your language. And then some follow-on work like abstracting abstract machines, it systematized that. It said, you write down your concrete semantics, follow this recipe, and out pops an abstract semantics. You still need to implement it, but that's a pretty big step. And then later work, like abstracting definitional interpreters, allowed you to reuse your implementation artifacts for your concrete semantics in your abstract. And then follow-on work to that came up or brought components that you could assemble, and the assembly was sound by construction. So now you've got formulation and an implementation that are verified sound. So there's just been a lot of good work to make CFA, the construction of CFA, less expensive in those regards. So what demand CFA addresses is the pricing model. The pricing model of CFA is not very accommodating. And the reason is that, well, here's what I mean by pricing model. You've got a control flow analysis, you've got a program, and what you're going to do is you're going to send the control flow analysis off on the program and maybe later get back this huge bundle of facts. The bundle of facts we saw on the first slide. And I say maybe because there are a lot of things that could go awry. So first, you might just time out. It might just take too long. And that's like pretty standard. It's hard, it's very hard to tell up front whether your analysis is going to come back in 1 minute or 3 days for a program. And then of course, your analyzer might have bugs in it. and if you hit a fatal bug during analysis, that's it. You might have some information that you can recover, like that you've learned up to that point, but you have no guarantees about whether it's a conservative approximation or not. And then you really need to handle the whole language, because if you encounter a part of the language or a primitive that the analyzer doesn't handle and it just kind of throws an error, that's it. You've tanked the entire analysis. So all of these are real. All of these, I was in Matt Might's lab and we were writing analyses and running them on Java programs for a particular project, and we hit like all of these. Okay, so basically the situation is that failure is catastrophic and it's just always looming. And then there's the case where, what if you run your analysis and it comes back and you don't get any actionable information? That's going to be true of any static analysis you get. Maybe the answers you get are not precise enough to be actionable. Well, what if you turned up the context sensitivity, turned up the precision? It cost more, but maybe that would be enough. Are you willing to do the analysis again just to see? And so this pricing model, this sort of monolithic bundle of facts that you get, it basically means you can't use CFA in interactive contexts, and you can't run it at multiple stages. So like the canonical place that you deploy CFA is in the compiler, and you have to pick where in the compiler you want to run this analysis, and then the compiler is going to transform the program, and what happens to your analysis information? You've got is it just obsolete? Maybe you can correspond it somehow. It's just too expensive. And then finally, what question are you going to ask about the program? Because the analysis is going to answer that question for the whole program. So it might be a simple flow question. What flows in these expressions? It might be questions about the ranges that numeric values can take on, that kind of thing. But basically, you have just a fixed set of questions that you're going to ask of the entire program. If you want to answer other questions, you need to fold them into this big monolithic analysis. Okay, so contra all of these points, this is where I think demand CFA fits. It produces per query control flow information relatively cheaply. So you pick a point in the program and you ask a specific question, and it will resolve that question as locally as possible. And so you're still susceptible to timeouts, you're still susceptible to bugs and to unhandled language features, but it's not catastrophic. Because if it fails there, you move on and you try somewhere else. Or if it fails there, maybe you don't get actionable information, maybe it is feasible to just increase the context sensitivity and say, maybe we should increase the precision and that would be enough. So when you have the ability to cheaply answer these questions, or potentially cheaply answer them, then it becomes feasible and viable to use it in interactive contexts. And now you can work with other tools to answer questions about your program and actually have a conversation. It also becomes feasible to just run it on the code you have. So you could run it in your compiler makes some transformations of code, run it on the transformed code. Or if you're running it in an editor for a user and the user modifies the program, run on the modified program. Also in an editor, often the program is not complete. That's a big problem if you have an exhaustive analysis, but it's possible to answer questions about incomplete programs when you don't touch the incomplete parts. And then finally, if you're just asking these one-off queries, then you can ask different questions at different program points. And you don't have to decide up front all of the answers, the kinds of answers that you want. So I just want to,
I will just add another point here. So there is the sense in which it is we're running one big atomic thing. But there's also the implementation perspective, which is that your implementation has to be one big atomic thing. Otherwise, it doesn't work. And so if you're like, I would like to, I have this one question that I want to answer in one place, and I would just like a precise answer to this question on this easy subset of my programming language. It's very hard to use CFA to do that.
Yeah.
And it sounds like your approach is going to make this easier.
Well, yeah, I mean,
Because you have to, you are just saying, well, then I have to avoid having any unhandled language features over my whole language if I want this to be usable at all.
right. And you're talking about something that actually does show up in this, where it's because you have so many different kinds of questions you want to answer, and you're going to make this monolithic analysis implementation, that they say, well, we want something we can know is sound by construction. Okay, so, time's up. Yeah, I'm going to go over this real quick, just to illustrate how easy it is to analyze transformed code. So this, our factorial program, it turns out you can inline this function, and that's going to change the program. So I just want to go through the steps real quick of how the analyzer would do it. So you're going to resolve the query of what could be bound to k, and that's this lambda here. And then you'll see that it's safe to inline, so you're going to perform the inline, you're going to beta reduce. So now you've, I mean, it's sort of trivial, but like, you've modified the program. Now you're looking at a different program. And once you've inlined this lambda and beta reduce, this parameter k is useless. You don't need it. But you need to determine you don't need it. So you can actually run an analysis, a useless variable elimination analysis, which typically you need to run a full CFA for. And you can see, that k is only ever passed as an argument, that the callers of fact all agree, you can remove that third argument, that kind of thing. But it's feasible to do this, and it's just sort of these steps. Okay, so, and then Jeremy, you had a question. Will you remind me of your question?
I guess I was just sort of curious about like, just from like sort of empirical evaluation of domain CFA.
Right. Yeah. Okay.
So how, like,
So what we did is we wanted to see if this sort of contention that you could write an analysis that didn't cover the full language, if that was actually feasible. So what we did is we hooked into the Racket linklet layer, and Racket's got like, is it still 1,000 or so primitives or more, just like lots. And in the analysis we tried, we didn't support mutation. We were aware of mutation, and so if something was affected by mutation, we could just fail. But we didn't analyze it. And we said, all right, how many places can we inline? How many places can we resolve the caller and prove that we can inline? And so we wrote this implementation, and it took us maybe like a month. And we covered maybe, there aren't many forms at the linklet layer. So we covered like the forms, but we only covered like a handful of primitives. And we ended up being able to resolve the function in function calls like 60% of the time. They were not there. They were not like immediate values. You know what I mean? Mm-hmm. And so, and then how many places you could actually inline with some fraction of that, like I'll say like a quarter of the time you could inline or something like that. So 60%. Like on the one hand, you say, well, that's like 40% you're missing. But really to only handle the small fraction of the language of the 60%, we consider that validation of the approach. I can get you the numbers if you're curious. I can get you
I guess I'm maybe less interested in the question of like, I can understand from your perspective why you're sort of interested in like, oh, can we still get a lot of bang for a buck if we haven't implemented everything? But I guess I'm more thinking from like a perspective of suppose, Microsoft has a giant team that's implementing both of these anyways, and the whole language, and the sky's the limit in terms of, what resources in terms of human development time for these compilers or whatever. But then, like, after we've done all that, are there some real differences between like demand CFA versus regular CFA? Like, and I think you're making some claims that yes, there are some important differences. I guess maybe one thing I'm seeing in terms of like core differences is like, well, there's this thing about like when you turn the knob on precision, it sounds like you're making this claim that with demand CFA, you could be, when you turn the knob to a higher precision, what happens to the amount of time? Does it grow sort of in a more even sort of linear way, or does it like skyrocket all of a sudden? Because it sounds like with KCFA, you could turn the knob because like you're not getting the answer you want, and then all of a sudden it like times out on you, and like you don't get sort of a nice.
Yeah,
Like that was an interesting claim.
Let me expand on this.
Yeah.
So 0 CFA is cubic. 1 CFA and higher is exponential.
Right.
And if you spend cubic time analyzing your program and you don't get, it's not precise enough to give you answers, or I'll just say you don't get actionable information and you're wondering if it's just not precise enough, are you willing to increase the context sensitivity and try again on the whole program? Maybe. It turns out that increasing context sensitivity, there's not some smooth ramp necessarily. On some programs, analysis time goes down, and on some it explodes. And
this is for CFA.
This is for CFA.
Okay.
And I mean, presumably the same for demand CFA.
Okay, well, I guess that's my question. Like, have you done any experiments with demand CFA to see what happens there, or is that?
Well, I have no reason to believe that it would be better fundamentally in terms of like, does it explode, does it not explode?
Okay.
It's just more feasible because it's just a single query of maybe thousands you're going to do to say, you run it, you don't get enough information, and you say, all right, I mean, I was doing 1,000 queries, I'll do 1,001. I'll try another one. You get a timeout on it so this doesn't go forever. And just to see, it's a little speculative. And if the delta is just, 0.1% rather than we do this whole thing again, it's just a lot more, you can respond a lot more to the program.
Is it that, so you're saying it still goes exponential, but I guess what you're saying is that demand CFA is more likely to just, per query, to look at a smaller part of the program, so the input to your exponential is a lot smaller, like maybe you're 2 to the n, but n is only 5,
well, yeah, I mean,
or 3 or something.
Yeah,
instead of like 20. Is that what you're saying? Or?
No, I mean, there's definitely that, and there's also, there are some demand queries that you can issue that really are going to ask questions of, the whole program. Queries issue sub-queries to get information, and it's just, the particular one you've asked involves a lot of the program, or it's a critical path or something like that. And so you could say, what I'm going to do is just put an effort bound on all of my query resolution, and when I hit one of those critical queries, I'm going to know because I'm just going to exhaust my bound. I'm going to give up. And so I'm going to get information on all the others. So you have a lot more, you basically can say, I'm willing to expend this much effort in total. And then with regular CFA, it's just kind of a gamble. Are you going to get results back or not? And it's a 0 or 1 thing. If it comes back, you got information. If it doesn't, you got none. With this, it's a sliding scale. For a given bound of effort, maybe you get 30% of the queries come back, maybe 50, and it's just maybe like a lower risk kind of thing.
All right, so by queries, you mean like for different program points, you're asking, each one you're asking a particular question.
Yeah, it's like if you're for a compiler, you want to inline everywhere you can. So you run your analysis, and then you're going to look at your analysis results and see where you can inline. Same thing with the demand. At every call site, you're going to say, can I inline? Can I inline? Can I inline? So you're going to ask all these questions. They're just sort of decoupled.
So if you are asking if you're only doing one query on a large program, then demand CFA is going to be radically faster because you're going to, in almost every case it's, but if you're doing queries on, similarly, if you do a query on every single program point for the things that flow to that program point, you're going to compute the whole CFA information and probably less efficiently.
It is a higher constant factor. That's if you let them run without that.
Can you share information so that if you're doing what you just described for a compiler and asking what flows to every single call site, can you avoid, you're going to have to recompute in some sense a lot of things, and can you avoid wasting work?
Oh yeah, most definitely.
By
So, like,
sharing the results of queries from between those subqueries.
Is this a dynamic programming?
Yeah.
Yeah. So like query 1 here is, where's K bound? And then that spawns query 2 and then query 3. Query 4 is where's K bound? And you get to the same place where query 2 is, hey, where is this lambda flag? And like that's sharing within the resolution of one query, but then you can just maintain the cache, the program doesn't change, and then later queries will have the answers already.
So just straightforward query caching
Yes.
gets you back a lot of what you want.
Yeah, and you can even be smarter in some cases. Yeah.
Is demand CFA like incremental? And I mean that in the sense of like incremental algorithms. Like let's say the program changes, how much do you have to recompute?
Yeah, we have looked at that a little bit. I've had an undergraduate student looking at that. As of now, we just, you can look at the footprint of a query, and you can know if it overlaps with the modified code. So we've done that. But in terms of like evicting the stale information from the cache, we're working on that. Okay. I really appreciate these questions. These are great. Any others?
So, if it's appropriate, so I heard rumors that you can think of CFA as like a data log program or program analysis in general as data log programs, or some kind of inference applying to fixed point kind of things.
Yeah.
Right. So, and I also heard rumors that if you want to have a data log-ish program, you could like do different ways to evaluate this program. Right. You could kind of do bottom-up fixed point, or you could try to be more demand-driven about it, whatever that means. So you see my question, right? Like, can I think of this, or maybe up to different ways of truncation? Does it arise out of these two things these two rumors composed, right? Where I take CFA, I treat it like a data log program, and say, okay, I have some data log engine that does fancy evaluation which applies to this particular data log program. Right. And then, maybe that's going to help me personally understand this edge thing, right? Like the locality of the analysis, where you don't have to go think about edge. Maybe that's just that you have maybe totally disjoint parts of the flows to or whatever calls relation, right? And so, if you only care about this particular query, you don't ever think about what flows into edge. It's just the lambda flows into K, but that's all you care about. Is that?
Yeah. All right. So just make sure we're on the same page. So you're using data log generally, right? Because like data log can express polynomial algorithms. So a lot of analyses you can't write in data log. But you're just kind of talking about like a data log style language.
Well,
like a
data
logic
log
language.
has, I think, so. Like I think maybe the polynomial part of data log is again, this is, maybe I'll rate myself a 2 out of 10 on now.
Okay,
but I think data log is polynomial when your terms are constant, right? You don't have function signals, right? So, and I imagine that once you want context sensitivity, you're going to have function symbols of maybe even different.
Gotcha.
Right. So I think that's where you just call it prologue, but that prologue was cut, right? So I just mean like data log was
Gotcha,
functional.
gotcha.
So maybe that's easy. The data log was functional.
Yeah, I was just wondering if it was like essential to your question. The data log aspect. No. Okay. No. So like, there's like the magic set transformation.
Yeah, that was one demand
Yeah.
driven way to run data log, right?
So I looked at that a while ago, and what came out was something like, it doesn't have to analyze the whole program, but it does have to sort of hit ground, which is like the entry point of the program. If you just take CFA semantics and kind of apply that, because for demand CFA we had to add a different kind of analysis. Like we added backwards analysis to it, and the backwards analysis didn't just like fall out from doing this like transformation on the forward semantics. So there are, like if you look in the literature, there is demand-driven program analysis on higher order programs that where it bootstraps by making a control flow graph from the program entry point, and then you sort of use that to drive queries, where to you hook into that for queries. And that's, I don't know if it's exactly what you get, but it's similar to that.
Okay, but here, I think you made it clear that your demand is your particular query, right? Not there's who knows where the program entry point is? Maybe
Right.
It's like it doesn't matter, right? So you don't know where the entry point is, right? So I don't know, I'm a fan of sort of trying to formulate things separately. So is there a version of demand-driven evaluation of data log function signals that could get you the thing you want? Obviously, you would have to tell this demand-driven data log the query you actually care about, which is not going to be about the program entry point, right?
Are you saying X plus demand-driven data log equals demand CFA, and you're wondering what X is?
Well, ideally, X is just like this other rumor, right? That CFA, there's a way to treat CFA, like to take a CFA problem, including the query, which is your part of inside there, and turn that into a data log program with some problem.
Yeah, I see. Yeah, I can't say any more about it than I.
Okay.
Yeah.
So what I think Kimball is pointing out is that the semantics aren't necessarily the same, and thus you can't necessarily get all the things that he's getting. So here's a sort of straightforward way to see that. Imagine that your program features the code that Kimball showed under a lambda, and that lambda is never invoked and immediately discarded. Then what things flow to any of those values? Like nothing flows to them. In the standard formulation of CFA is that we take a concrete semantics, and then we have an abstraction of that concrete semantics, and then it's at least plausible that a CFA would find empty sets for many of these variables. Not necessarily, like the conservative analysis is that they could think stuff could still happen. But if the CFA finds empty sets for all of these because it's dead,
Right, and the demand-driven whatever is not allowed to find any non-empty set.
well, then your version of the demand, then a demand-driven reformulation of that same semantics
Right, better find empty.
had better find
Right.
the empty set.
Yeah.
Whereas
Yeah.
if you just take this code, what you want in an editor is that it doesn't look at the
Right.
fact that this
Right.
code is dead at all.
Yeah. Yeah.
For a variety of reasons,
Yeah.
but one of which is that involves the whole program. And so in that sense, you're not going to.
Yeah, so it's interesting that your nice example also involves the program entry point, right?
Yeah.
It's never called, right?
Yeah.
So, I guess, when you first talk about edge, right? I have this idea that maybe what you're computing in a more modular way for query way is not the information that what you call CFA gives, but some kind of implication saying, well, if this were called, if this piece of code were invoked, then what will flow within this piece of code, right? So like, is there a way, and I don't know what people have thought about in terms of like kind of module evaluation of data, right? You want to pre-compute part of it and wait for the invocation call. I don't know.
Well, here what we need is a modular characterization of the semantics of the program.
Right. Yeah.
Which, I mean,
Yeah.
is a different way of saying a denotational characterization
Right.
of the semantics of the program.
Yeah.
But the tradition in the CFA literature is to start from an operational semantics and figure out how to generate an approximation of that, which is not, there's a sense in which demand CFA is answering a different question than that, which is part of why it's able to do different things.
What's the relationship with slicing? Like the backward slicing is sort of an old
Yeah.
thing, which I can't remember very well, but
Yeah,
it has sort of a similar feeling from 30,000 feet.
Yeah, so the way that we prove the sound is with an intermediate semantics, which is also demand driven, but it's concrete. And that semantics computes slices, which is just figuring out what parts of the program are relevant to a particular question. Okay, so future work. What we have is we can handle higher order control flow and environments. We can handle mutation, but we do it in sort of a brute force way, and it's not, when you reason about mutation, you have some notion of like flow sensitivity maybe in your head or path sensitivity even. We don't have that yet. So we want more human-like reasoning of just standard language features. We want to integrate first order theories, just to be able to reason about arithmetic and strings and all the primitives, but also maybe plug it into an interactive prover, which we feel like we can do because we can, it's low enough latency that we can actually dialogue with something else. And then, kind of the question you're asking, I want the ability to just turn the crank, and turn semantics into analyses, and a better understanding of the answer to your question would be informative there, I think. Like, what's the fundamental nature of like the semantics that we deal with? And then, as I said earlier, as I mentioned, the constant factor on demand is higher. And sometimes you do have a block of code and you know that you want answers for the whole thing. And so to be able to do an exhaustive analysis there, but then if there's any sort of free variables, anything you need to resolve outside, kick off to demand, that could be interesting. And then finally, integrating it with ML models to, all analyses have all these knobs. And who's turning the knobs? Nobody ever turns the knobs. But if we had models turn the knobs, but also a sound analysis is sort of like complementary to a lot of ML models. The ML models give you a lot of like heuristic judgment, but the sound analysis gives you like this really good epistemology. And so I think combining that would be pretty fruitful. And I'd love to hear any ideas that you have where we can take it. But I really appreciate your attention and your comments and everything. Thank you.
I have a less technical question. Sure. Because you keep saying human-like, so I think this is a school where people once built a Python interpreter that makes human-like mistakes in interpreting Python programs. So I was wondering whether you can also make your analysis make human-like mistakes.
Sure. I know. I considered saying maybe how a rational program would behave, something like that.
So rational.
It could be fun to have one that makes unsound
Bad
judgments.
inlining decisions.
Yeah. Well, like you could compare that with mutation, with like ignore mutation switch. Like this really isn't mutated in an important way while I care about this question. I promise. I mean, that could be interesting. Like that is in some ways what an aspect of human-like analysis of mutation is like.
Ignore it.
Is this, so That, yes, but also,
Like, have
but,
variance about
but if you might look at it and say, well, is this mutated? Well, yes, but it's not mutated while this thing that I'm asking the question about is happening, and so I'm going to ignore the mutation. And there's a sense in which that is demand driven. Like, I'm going to look and then look, like, is it possible that this is mutated during the scope that I care about? Okay, no. Now I'm going to ignore the mutation. And that is a sound way of approaching an analysis. Or is this mutated in is this ever mutated in some concurrent context? No, so then I don't have to worry about all the pain that brings.
So, I guess I want to ask some more about the human-like nature. So, I mean, you talked a lot about the benefits, in terms of performance and, smaller queries and so forth. But I guess, do you also think that since the demand, like at the beginning of the talk, you said, how would Sam do it? And this is the same way. Does that mean that you think that the analysis is more predictable, or it's easier for a human to understand, what will or won't work, or any human-like and that kind of more, good for humans in
Liked by humans.
What?
Liked by humans. Human.
Right. Yeah. Right.
I mean, or imagine you're using this analysis maybe for like security vulnerabilities or something like that. And and maybe there's an engineer whose job is to like, okay, you've got 100 reports from this analysis tool saying, oh, here's 100 potential vulnerabilities, and I have to wade through all these things.
Right.
Are they easier to read and wade through or grok, for that?
Yeah.
Right.
Maybe. I mean,
That's a really interesting question. Something I envy about type systems is you have this really clean interface with like the programmer, I mean, I'd say a good feature, maybe you disagree, but a good feature of a type system is that you can sort of internalize it. That doesn't feel so like that there's some small simple model you can use.
Sure.
And you can know that your program's going to type check. And most analyses in the wild are so ad hoc that like you don't know if it's going to come back with a precise answer or not.
Right.
Change your program in a subtle way. So that's a really interesting question of if this is really how you would go about it, it's just doing it faster or something.
Right.
Yeah, intuition matches that. That's interesting. I'll look at that.
And of course, one of the issues with type systems is that when people try to make their type checker smarter by doing like crazy things that a human wouldn't do, then of course more things type check, but then when it doesn't type check, you're just like, oh my god.
Yeah, I mean, this is one of the major problems with type bracket is that type bracket does not provide you with it provides you with the experience that you write down a bracket program, you add some types and then it type checks and you're like, wow, that worked. But it also provides you with the experience that this thing worked, but this very similar thing doesn't work and I have no idea why. And there is a real tension between those two features.
Like one possibility is you just make nothing work.
Yes.
Yeah. But it's at least nice if, when something doesn't work, you kind of say, well, I guess that makes sense.
Yes.
Okay.
Okay, thanks again.
Thanks, Al.